Hey everyone, today we'll be talking about function decomposition. Sometimes in college algebra, you'll be given a function, like the one h in this example here, and you'll be asked to find two other functions whose composition is h. In some sense, you're imagining that h was created in the first place by composition and undoing the steps that led to that final function. Now, this undoing analogy isn't quite perfect because, as you might imagine, you can do this in an infinite number of ways. For example, I could put, as the first function, I could map 1 to chicken, and then 2 to this little drawing of a spider, and so on and so forth. Just put literally anything in the sort of middle step, the layover step. Even if I restricted myself to numbers, there's still an infinite number of possibilities. I can make this 53.2, I could make this 10/7, and so on. But most often when you see these types of problems, there's going to be one or two choices that are somehow natural or evident. In this case, h takes each number in the input set, multiplies it by 20, and adds 1. For example, 1 times 20 is 20, and then plus 1 is 21, and 2 times 20 is 40, plus 1 is 41, and so on. So in this case, the natural sort of decomposition would be mapping 1 to 20 first, as in that's sort of the first step you're going to do when you're going through this function mapping, this flight plan, right? The natural intermediate step is going to 20 and then to 21. You know, kind of like if you're trying to get from San Francisco to Phoenix, there's a natural layover in Los Angeles, as opposed to, say, Beijing. So for this decomposition, I'm going to have f map 1 to 20, map 2 to 40, map 3 to 60, and 4 to 80, and then have g map each of those to the final destinations. And you can verify that the function h is equivalent to the combination of these two, to following the f flight plan and then the g flight plan, no matter what airport you start at. Okay, let's do an example using functions defined by rules that makes this logic a little bit clearer. For example 2, let's say we've got a function. It's called k, and it inputs from whole numbers, c, and it outputs numbers. So, pretty standard and nice function. And its mapping is defined by n being sent to n plus 1 cubed. Now the natural decomposition here is to separate the action of adding 1 from the action of cubing, right? Each of those represents a distinct step in this mapping. So we'll have k separating into two piece functions, L and J. The first one should be the action of adding 1, right? So J is going to take in the input from the same input set as k. It's going to output a number, and its mapping will be that addition of 1 that we described. Now L, following up on that, will take in the numbers outputted by J, map them to the final destination of K, and its action is going to be that cubing action that we left out from the first function. So, L of J will be J cubed. And in fact, we can verify that L of J of n is equal to L of n plus 1, or n plus 1 cubed, which is equal to k of n, just as we want. So that's good. If you're still having trouble with the intuition of this, I suggest you draw a little diagram like this. Maybe have n equals 1, see where j maps it, and then see where L maps it. That should help you out. All right, final example. Let's say we've got a function g that takes in positive numbers, or are positive, and just outputs numbers. So again, pretty standard function. And it's going to have its mapping defined by g of x equals to the square root of x, then plus 1, and then squared. The emphasis here is that there are essentially 3 different steps that x goes through, right? First, there's a square root, and then you add 1, and then you've got the square. And of course, there's multiple natural ways to split those up. I'm going to showcase one way using 2 functions. I'm going to call them I and j. And I, like usual, has the same input as g, so are positive or positive numbers. And we won't specify the codomain too strictly, we'll just say it outputs numbers. And I is going to encapsulate the square root step. So I will have I of x be the square root of x. Now j will input out of i's output and go to the same place that g sends its numbers. And it is going to include both the other steps. So j of I will be I, including the +1 step, and then including the squaring step. And once again, you can check g of x is equal to square root of x plus 1 squared, and j of I of x is equal to j of the square root of x, which is equal to the square root of x plus 1 squared, just as we need. Once again, this is only one of the natural ways to do this, so if you're watching at home, I encourage you to come up with another one if you're still having trouble with this concept. As a final note, I just want to point out that I've chosen functions here where domain won't really be a big issue, but that, once again, you should be thinking more closely about domain anytime you're working with functions, because that kind of thing can really trip you up. All right, that is it for today. Thank you all for watching.